So let's take a look at some properties of continuity. We have a couple of continuous functions at a particular point, and c being a real number. If c is a real number and f and g are both continuous at x equals a, and then we have this extra statement here, f is continuous at g of a, that's going to be because of a composition that we're going to do in a minute. Then the following are also continuous at a. You know what? I don't think there's enough screen real estate here to list out all these properties. So, I'm just going to turn this a little bit. I'm going to turn this sideways. So it says the same thing. It's just, it's sideways over here. So I have room to write stuff like, well, here's our first one. It's a constant multiple. So let's say we have a function and we multiply that function by, 2. Well, it just makes all of our y values twice as big as they used to be. Does that destroy continuity? No, it doesn't make any holes in your graph. It doesn't make any gaps. It doesn't make any vertical asymptotes. So it's still continuous. How about add and subtracting your two functions? You have two continuous functions and you add or subtract them. That is not going to create any kind of holes, gaps, or vertical asymptotes, right? Because you're just adding or subtracting whole numbers, or not even whole numbers, just function values. We can do the same thing with multiplication. When we multiply our two functions point by point, it preserves continuity. We can also divide them point by point, and it still preserves continuity, as long as the denominator there, of course, is not 0, because then we run into the point where we could create a discontinuity. If it is 0 over 0, it is more than likely a whole. If it is some number that's not 0 over 0, it would make a vertical asymptote. What else can we do? Composition does not destroy continuity. And here's the reason why it says f is continuous at g of a. So we've stuck in a into the g of x function. We got some output value, and we wanted to make sure that actually f is continuous at that particular point. So composition still preserves continuity, and then we have one more, and that's taking the inverse of our function. As long as our function is 1-to-1, remember that what an inverse does is just switches inputs and outputs. So if you have those original points and you just switch your x's and your y's, it doesn't make any new holes, it doesn't make any gaps, and it doesn't make asymptotes. If you look at all of these properties, they look pretty familiar, and they should, because they're based on the properties, the limit laws. And since continuity is defined in terms of limits, I think that should make sense. Okay, let's look at example 5. Determine the intervals over which each function is continuous. So we've got a variety of different things. We've got, let's say, a polynomial, we've got rational, we've got radical, we've got trigonometric, inverse trigonometric, exponential, and logarithm. So when we're talking about the intervals over which this function is continuous, again, it's about, first of all, where is the function defined? And does the limit exist at all those points? In other words, we don't have any gaps and we don't have any asymptotes. We don't have any points of discontinuity. And we want to make sure that the function and the limit match up. Well, the first one here, it's a parabola, and it's defined everywhere, right? It's just some sort of parabola. Breep. Yep. I don't need to actually graph it. I know it's defined everywhere. There's no holes, there's no gaps or anything. This is continuous on the open interval from negative infinity to positive infinity. Okay, on number 2, we have a rational function. So this rational function does have an asymptote. It has an asymptote at x is equal to -1. However, I need to make sure that that's an asymptote and not like a hole, right? I don't know. So one of the ways that I could do that is if this was a hole, that factor needs to be shared up top. If it was shared up top, that means it would be evenly divisible by it. So you can either factor the top if you wanted to, or I can do a little synthetic division over here by -1 and see if it goes in evenly. I'm going to do that because it might be a little faster. -7, bring down this 2, multiply, I'd get -2. Add those things together, I get -7, multiply, I get 7, I get 0. Oh, it does go in evenly. In other words, this was equal to let's see, 2x minus 7 times x plus 1, x plus 1. So it's still not defined at 1, but it has a point of discontinuity at that particular point, which means that the function is going to be continuous everywhere outside of that one particular point. So it's going to be from negative infinity up to negative 1 union negative 1 to infinity. All right, let's keep going. We've got this square root function, this radical function, and we have a quadratic underneath it. So in order to see where this thing might be continuous, we need to make sure it, like wherever it's defined, it's like its domain, right? So it's a square root, so I need to make sure that all of this stuff is positive inside there. So we did that back there on that previous question. I'm going to do it again. I'm going to need some more space. I need to make sure that x squared minus 5x minus 7 is greater than or equal to 0. You know, it's totally convenient that we just factored this thing right up here because it's the exact same quadratic. So we know exactly how it factors, but once again, we want to make sure, let's see, minus 7. We want to make sure that it's the equation, first of all, x plus 1 is equal to 0. And then we get our two critical points. X is equal to, let's see, 3.5, 7 halves. Or negative 1. So if I put those things on a number line, let's see, a 0, let's say a negative 1, and a 3.5, approximately right there. Those things get closed circles because it's okay if your square root is, 0. And now we just want to do a little test value. 0, of course, is the easiest one. Let's see if this works, though. Let's use Mr. LaBelle's little shortcut. This is a great OR, so it should be an OR inequality, which is on the outside. So let's test it. If I plug in 0, it should make this a false statement. So if I plug in, let's say, a 0 into the factored form, I think it's faster and easier. 2 times 0, 0 minus 7 is a negative 7. And let's see, that would be a positive 1. I get negative 7 times 1 is negative 7 is greater than or equal to 0. That is a false statement, so we know that it should be on the outside. Which means that this should be continuous from negative infinity up to negative 1. And then it's going to have, it can actually, it'll be continuous from, let's say, from the left at negative 1 there. It's going to have a big gap in between it. And then it'll do the second branch of that graph, whatever that thing looks like, from 3.5 to infinity. So think about what we're actually finding here, right? It's going to be important for the conclusion of this example here. So for tangent. So tangents, maybe a look at the graph of tangent. Surely we're familiar with that graph, right? So we have vertical asymptotes all over the place. Something like this. And then let's say that I throw in these little tangent curly cues, whatever. They kind of look like a cubic graph. They're not, though, because they're enclosed within some vertical asymptotes. And so this is the number, negative pi over 2 to pi over 2. It's continuous everywhere in between those two things. And then it's continuous from pi over 2 to the next one here, which is 3 pi over 2. And then back over here on the other side, on the left side, negative pi over 2, that's the right side of this. And then the next one would be a negative 3 pi over 2. So one of the ways that you could list out where it's continuous is just by some sort of pattern. So I could do ... to start the pattern, negative 3 pi over 2 to negative pi over 2, comma, union, negative pi over 2 to pi over 2, union, and then do maybe one more to make sure that we establish that pattern, pi over 2 to 3 pi over 2. And actually, that should have an extra little union symbol up here. There we go. What did we just find there? Sure, we found where it was continuous, but isn't that the domain of that function? What about the arctangent one? So the arctangent graph is basically taking just this piece here and flipping it across the line y equals x. So its graph looks like burp with two horizontal asymptotes and well, maybe purple. All right, and then here's the graph. Where's this thing continuous? It doesn't matter. It has horizontal asymptotes. It's continuous everywhere. It is continuous from negative infinity to infinity. All right, and let's see, e to the x. You know what? I already have this graphed. It's right up here. It's right here. Here's e to the x. Is there any place where this thing is not continuous? There's no gaps. There's no holes. There's no vertical asymptotes. This exponential is continuous everywhere. What about the natural log of x? Hey, that's the graph that's right underneath this one. And this one is approaching the x-axis, but there's a vertical asymptote. There's a vertical asymptote right there at 0, so it's definitely not continuous there, but it is everywhere else to the right of it. And there's nothing that exists over there on the left side. So this one is in open parentheses, 0 to infinity. So one more time, notice that basically what we just found in each of these cases was the domain. What that means is that for all of these types of functions, they're all continuous at every single point in their domain. And so that's where we're going to conclude this. They're continuous at every single point in their domain. That first one there is a polynomial function. Yep, always continuous. Well, for polynomials, that's continuous everywhere. And so this is very, very important that we can use in particular free response questions. For example, continuity as a requirement for something. If it's a polynomial function, I can just point out, because it's a polynomial, it's continuous everywhere. And then I have that condition met. What do we have on number 2? That's a rational function. As long as the points that we're talking about are within the domain, it's continuous there. Of course, we take out our holes, we take out our vertical asymptotes. Number 3 is a radical function. It's continuous everywhere in its domain. We got trigonometric for number 4. We have inverse trigonometric for number 5. We have exponential, and we have logarithmic. So all of these functions, they're going to be continuous at every single point in their domain. And again, like I said, if continuity is such a big thing and we have to make sure, like it's a checkbox, so we have to check off for different functions, we can just point out, hey, we have ourselves a exponential function, which is continuous everywhere. Therefore, that requirement has been satisfied. Okay, so essentially, this is what has been allowing us to do direct substitution to evaluate each one of those limits. Because remember, that just simply means that the value of the limit and the value of the function are exactly the same.